My name is Jared Coleman, and I'll be presenting our work on network synthesis for dispersed computing in the Internet of Battlefield Things. Modern tactical operations require the ability to rapidly synthesize networks of mobile compute nodes for gathering data through IoT sensors and monitors, processing it either at base stations or at mobile compute nodes closer to the edge, and finally, disseminating both raw and processed data to other nodes in the network. Since we cannot hope to deploy sensors and compute nodes everywhere, synthesized networks must effectively balance efficiency and cost. Efficiency metrics may include task execution makespan, which is the total time to execute a given task on the network, or other metrics. The cost factor could also be interpreted in many ways. In the example later in the presentation, we'll use a combination of deploy cost and risk. So the problem we aim to solve is given a set or distribution of tasks defined as directed acyclic graphs of dependency-linked compute tasks and a mother network of all possibly deployable nodes with different communication speeds, bandwidths, deploy costs, and risk. Our goal is to find a subset of that mother network which best balances deploy cost, risk, and makespan according to a given cost function. In order to put all these pieces together, we developed a general framework for these kinds of network synthesis problems. The framework essentially allows users to mix and match different optimizers, schedulers, mother networks, task sets, and cost functions to suit their application's needs. To give a more concrete instance of the problem, consider this mother network with high or low speed compute nodes and high or low speed communication links. The cost of including a node or communication link in the deployable network is a function of its speed and type. Then, consider a set of 5 unique tasks. Each task is modeled as a directed acyclic task graph, where an edge indicates that the output of one subtask is the input to another. We use the heft scheduler to schedule task graphs over the network, assigning certain subtasks to run on certain nodes in the network. The schedule considers the time to execute and route input and output data across the network. Finally, for the purpose of demonstration, we consider a very simple brute force optimizer, which will compute the average makespan of the tasks over every possible subnetwork of the mother network. Finally, to see the network synthesis in action. Here's the output of our framework for the example problem. In the top 2 left panels are the current subnetwork and task being analyzed. For each subnetwork, the heft scheduler is used to compute the average makespan over all 5 tasks. These results are then plotted in the bottom left panel, and the best networks, according to different acceptable deploy cost and risk, are displayed in the remaining 3 panels. We hope to leverage our general purpose framework to support larger networks and applications by implementing better optimizers, like simulated annealing, and better schedulers, since heft is a bottleneck in the optimization currently. Also, we hope to consider more diverse and even dynamic networks,